Hello, I welcome you all in this course on power plant engineering. Today we will we'll solve certain problems in this session. The first problem is an input output curve of a 10 megawatt station, that is power station, is expressed as follows: I is equal to 4 into 10 to power 6, 10L plus 8L plus 0.4 L square. This is load in megawatts, input in kilojoules per hour. Without plotting any curve, find load at which the maximum efficiency occurs. So, first of all, the efficiency for maximum efficiency has to be found out. Another is find the increase in input required to increase station output from 3 to 5 megawatt by means of input output curve and also by incremental rate curve. So, by both the methods, we have to find the change in the input energy from 3 megawatt to 5 megawatt. So, start with the maximum efficiency. Okay. So, we have the equation I is equal to 4 into 10 to power 6, 10 plus 8L plus 0.4 L square. Now, we will take I by L, 4 into 10 to power 6, 10 by L plus 8 plus 0.4 L. Now, efficiency is L by I. So, we will reverse it, right. So, it will become 1 by 4 into 10 to power 6, 10 by L plus 8 plus 0.4 L. Now, efficiency is going to be the maximum when this is minimum, right. So, let us differentiate it. D by dl 10 by L plus 0 plus 8 plus 0.4 L. Now, when we are differentiating this equation, then this will become minus 10 L square. This is a constant, 8 is a constant, so it will be 0 plus 0.4 is equal to 0. Or we can say 10 by L square is equal to 0.4, L square is equal to 10 by 0.4 is equal to 25, L is equal to 5. So, when L is equal to 5, the efficiency is maximum. At this load, the efficiency is maximum. That is the first part of the numerical. Now, the another part is find the increase in input required to increase station output from 3 to 5. Now, because now the station output is suppose is giving 3 megawatt, I want to increase the output to the 5 megawatt. How much input has to be increased so that I get the 5 megawatt output? And there are two methods: input output curve, where is first is input output curve, where there is a output and input curve, and with the help of this curve you can find out how much input is required. This is output and this is input, right. So, for the change in the output you can find the change in the input, but I do not have any input output curve, right, and also by incremental rate of curve. So, for this purpose we know that L is equal to 3 megawatt. Now, we will put L is equal to 3 megawatt into the equation, we will put L is equal to 5 megawatt in the equation, and we will find the change in the input. That is the only way. So, when L is equal to 3 megawatt, so this is I 3 is going to be equal to 4 into 10 to power 6, 10 plus 8 into 3 megawatt plus 0.4 into 3 square, and this will be equal to 150.4 into 10 to power 6 kilojoules per hour, because I is expressed in kilojoules per hour. Now, I 5, when input for 5 megawatt output, it is 4 into 10 to power 6, 10 plus 8 into 5 plus 4 into 5 square. Now, this gives I 5 as 240 into 10 to power 6 kilojoules per hour, right? Now we have inputs for both the cases. I mean for 3 megawatt and this is for 5 megawatt. Now we can take the difference delta I is equal to 240 into 10 to power 6 minus 150.4 into 10 to power 6 and it comes around 89.6 into 10 to power 6 kilojoules per hour. Okay. Now there is an incremental rate curve also. If you use incremental, because I equation for I is given, it is 4 into 10 to power 6 10 plus 8L plus 0.4 L square. Now incremental rate IR is di by dl. So 4 into 10 to power 6 8 plus 0.8 L. Now 0.8 L means 4 into 10 to power 6 8 plus 0.8. We take L, the value of L as 3 plus 5 by 2, it is equal to 4, right? And in this case, when L is equal to 4, the incremental rate is 4 into 10 to power 6, 8 plus 3.2 is equal to 4 into 10 to power 6 into 11.2. And then increase is equal to 4 into 10 to power 6 into 11.2. 5 minus 3 is equal to 89.6 into 10 to power 6. So, in both the cases you are getting the same increment in the input. Now, numerical number 2. The numerical number 2, there are two power stations X and Y and supplied to a system whose load is 120 megawatt. So, the system load is 120 megawatt and there are two systems X and Y. They are sharing the power of 120 megawatt, right? And minimum load is 12 megawatt. 12 megawatt is the minimum load during the year. The estimated cost of these are as follows. Cx is 120 into kilowatts plus 0.028 kilowatt hours. Cy is 115 into kilowatt plus 0.032 kilowatt hours. If the load varies as straight line, find the minimum cost of generation. Load varies as straight line means starting from here, minimum load is 12 and maximum load is 12, maximum load is 120 megawatt. So, this is 120 and this variation is straight. It is 8760 hours. This is for the entire year, right? If the load varies in a straight line, find the minimum cost of generation, installation capacity of each station, annual load factor, capacity factor and use factor for each machine, the average cost of production per kilowatt hour for the entire system. Now, we will start with Cx is equal to 120 plus 0.028. Cx is equal to 120 plus 0.028. This is kilowatt and this is kilowatt hours, right? And C2, Cx, this is Cy, this is Cx. Cy is 115, 0.032. 115, 0.032, right? And this cost is in rupees, both are in rupees as shown here. Cx is in rupees and Cy is in rupees. Now, we have to find the value of H. So, H is equal to A1 minus A2 divided by B2 minus B1. So, A1 minus A2 is 120 minus 115 divided by 0.032 0.028 and this is equal to 1250. So, for the duration of 1250, we will draw here 1250, it will come somewhere here. For 1250 hours, there is going to be a peak load plant and one is going to be the base load plant. So, which one out of these two will be the base load plant? This is going to be the base load plant, this is going to be the peak load plant. Right. After identifying this, we have to find P base. Now, P base, so 120 minus P base, 120 minus P base divided by 120 minus 12. This divided by this is equal to this divided by this, right. So, it is equal to 1250 divided by 8760. And if you manipulate this, you will find that it is equal to 120 minus 120 minus 12, 1250 by 8760, it is going to be 105 megawatt. So, 105 megawatt is the cutoff line, it is the capacity of the base load plant, and beyond that it is a peak load plant. Now, installation capacity of another system, peak load plant. So, peak load capacity is, it is 120 minus 105, it is 115, sorry 15, 120 minus 105 is equal to 15, right. Now, here in this question, if we assume that reservoir capacity is 22%. There is a reservoir which can have the capacity equivalent to 22%. In that case, the peak power is going to be 15 into 1.22 and it is going to be 18.3 kilowatt. Okay. Now, after that we have to find annual load factor, capacity factor and use factor. So, load factor is equal to actual unit generated divided by the maximum possible unit which can be generated or the capacity of the plant. So, actual unit generated divided by the base plant capacity or power base into 8760. Power base is 105, so 105 has to be multiplied by 8760. That is the energy which base plant can always generate throughout the year. So, it is coming as half 1250 plus 8760 plus 105 plus 12, sorry, this is okay, half 1250 plus 8760 plus 105 plus 12 plus 12 into 8760 divided by 105 into 8760, right, and this gives the load factor as 465,465 plus 105, 120, 919, 800, 0.62 is equal to 62%. That is the load factor, and there is a reserve capacity, as I said it is 22%, right, but there is no reserve capacity for the base load plant. The reserve capacity is only for the peak load plant, it is not for the base load plant. So, the capacity factor, regarding the capacity factor is equal to load factor is equal to 62% for base load plant. So, total unit for both the plants is equal to 570.8585 into 10 to power 6 plus 9.375 into 10 to power 6 is equal to 580 into 10 to power 6 kilowatt hour. So, total generation cost C is equal to Cx plus Cy is equal to 28.57 into 10 to power 6 plus 2.25 into 10 to power 6 is equal to 30.595 into 10 to power 6. And it has to be divided by, if you want to have the unit cost, then it has to be divided by 580 into 10 to power 6 and it will come around 0.0527 or 5.3 paisa per unit or per kilowatt hour. Okay. So, this is, we have calculated the average cost of production per kilowatt hour. Actually, in this case, the area has to be calculated. Simply, it is a area calculation driven numerical. If you calculate this area, you will find that this is the energy produced by the yearly energy produced by the base load plant. So, take the entire area minus this area will give you the energy, this energy, and this is how you can calculate. Either you take the area of this triangle or area of the bigger triangle minus this area. This will give you the. So, you can have many combinations of finding out a solution of this problem. It will depend how you by which method you calculate the area. Okay, and the next numerical is about, again, on the economics of the power plants. The incremental fuel cost for 2 generator units of a power plants are given by dF1 by dP1. This is incremental fuel cost. It is dF1 by dP1 is equal to 0.07 P1 plus 25 and dF2 by dP2 is equal to 0.07 P2 plus 22. F is the fuel cost and P is the power in megawatt. Find economical loading for the 2 units when total load supplied by the power plant is 180 kilowatt. Loss in fuel cost per hour if load is equally shared by both units. So, these 2 things have to be found out or have to be driven out of these data. So, simply, first of all, first of all, we will take that P1 plus P2 is equal to 180. It is given here 180 kilowatt, right. For economic loading, this has to be equal to this. So, dF1 by dP1 is equal to dF2 by dP2 for economic loading. Now, we are putting these values 0.07 P1 plus 24 is equal to 0.075 P2 plus 22. Now, from here we can always put from here P2 is equal to 180 minus P1. So, 0.07 P1 plus 24 is equal to 0.075 180 minus P1 plus 22, right. Now, this gives 0.7 P1 plus 24 is equal to 13.5 minus 0.075 P1 plus 22, 0.145 P1 is equal to 11.5 or P1 is equal to, or capital, it is capital P. So, P1 is equal to 115 divided by 0.145. No, it is equal to 79.3 megawatt. So this is P1. So P1 is 79.3 megawatt, right? Now P2 is equal to 180 minus P1 is equal to 100.7 megawatt. So this is so P1 is 79.3 megawatt. Sorry, this is P2. P2 is 107 megawatt. Total is 180. Not it is megawatt. I think it is kilowatt. Kilowatt. So it is this kilowatt and this is this kilowatt. Right. So total is 100 kilowatt. 180 kilowatt. Now yes. Now the author wants to know if we divide this 90, we'll make this 90 and we also make this 90. Then how it is going to affect the fuel cost or change in the fuel consumption. So for this purpose, suppose the load is equally shared. So load is equally shared means 180 by 2 is equal to 90. So unit 1. Unit 1 increase in cost. Now increase in cost unit 1 is equal to 79.3 to 90 because we have increased the fuel consumption is equal to 0.07 P1 plus 24 dP1. We have integrated it, right. So once we integrate, because power is the output, power is the output. So once we integrate it, we get 0.07 P1 square by 2 plus 24 P1 79.3 to 90, and then it becomes 0.035 90 square minus 79.3 square plus 24 90 minus 79.3. Okay, and further simplifying this, we get 63.4 plus 256.8 is equal to 320.2 per hour. This is the fuel consumptions per hour has increased. Yes, and the next is unit 2. Now, what unit 2 is producing? Unit 2 is producing 107. Unit 2 is producing 107 kilowatt. Now, output of the unit 2 has to be reduced. So, we will start from 107, 100.7 to 90. 0.075 P2 plus 22 dP2, and that is equal to 0.075 by 2 P2 square plus 22 P2, 100.7 to 90, then 0.075 by 2 90 square minus 100.7 square plus 22 90 minus 100.7, right. So it is coming rupees minus 311.9 per hour, and previously it was coming 320.2, I think 320.2. This is positive, that is negative, and if you add these two, you will find that net increment cost 320.2 minus 311.9 is equal to rupees 8.3 per hour. That is the net increment of cost for running the system. Okay, that is almost all for today, and now we have complete all the lectures related with the course Power Plant Engineering. I hope all of you must have enjoyed these lectures. Now, after that, we will conduct the examination. The schedule will come later on, and I wish best of luck to all of you who are appearing in the examination. Thank you.